Hello and welcome to the next installment of trigonometry, where we're going to talk about the famous or infamous sine and cosine, two functions that we're going to be using a lot in the coming weeks. And so we're going to come up with rock solid definitions for these two functions and see how the unit circle comes into play, why we've spent so much time talking about the unit circle. And basically how do sine and cosine fit into the picture. Okay, so without further ado, let's go ahead and dive into talking about sine and cosine. Okay, so our learning objectives are to 1, define the two functions, sine and cosine, and then 2, compute sine and cosine using the unit circle and their definitions. And then lastly, we're going to derive and use a very important identity involving sine and cosine. Is called the Pythagorean identity, and we'll understand why it's called the Pythagorean identity when we come to it, and why it's useful with relating these two functions. Okay, so back in geometry class, you did learn about these two functions, sine and cosine, in the context of a right triangle. So you were working with right triangles, and you learned that the sine had to do with the opposite side and the hypotenuse, and the cosine involved the adjacent side and the hypotenuse. So suppose you've got an angle in the right triangle where it's not the right angle, so one of the two other angles. Then you define sine of theta is the ratio of the opposite side to the hypotenuse. So another way that people write this is sine is equal to opposite side divided by hypotenuse. Okay, so it's whatever the opposite side length is, and to find what's opposite and what's adjacent. Opposite is if you put yourself in the corner of theta and you look out, you'd be looking at the opposite wall. That would be the opposite side. So that's opposite, and the hypotenuse is the hypotenuse. It's the long side opposite the 90-degree angle. For cosine of theta, that's the other ratio involving the legs of the right triangle. That's the adjacent side. So I'll use another color. That's the adjacent side of your right triangle divided by the hypotenuse. And what's important about these ratios is that they remain the same no matter how big you scale the triangle. So it's really just dependent on that angle. If you make your triangle twice as big, you have the same ratio. And if you make your triangle half as small, so you shrink it down, then the ratio will still stay the same. This larger triangle with the same angles is going to have the same ratios, and that's because when all the angles are the same, the side lengths are just scaled up. Okay, so you can grow and shrink your triangle, keeping the angles the same. And so what will happen is those ratios remain the same. So sine is really just dependent on the angle, and cosine is really just dependent on the angle. If your triangle is bigger, then it doesn't matter how big the triangle is. If that angle is the same, you still get that same ratio. Okay, so it's independent of the size of your triangle. It just depends on the angle. Okay, so how do these fit into the unit circle? Well, we've already looked at right triangles. So let's go ahead and take a look more closely at these right triangles in our unit circle and apply the definition of sine and cosine as opposite over hypotenuse and adjacent over hypotenuse. So from our last page, we have the sine of theta. So I'm going to draw our angle theta in here. So here's our angle theta. So there's our angle. Then the sine of theta is going to be the opposite side, which is y. Opposite side divided by the hypotenuse. Since it's the unit circle, the hypotenuse is a length of 1. This is opposite over hypotenuse. Opposite over hypotenuse. Hypotenuse is 1, so we just get the side length y. So sine of the angle theta is equal to y, which is the height of that triangle. Cosine of theta is adjacent over hypotenuse. This is adjacent side. And the adjacent side, in this case, is equal to x. So the cosine of that angle is x over 1, which is our hypotenuse. So cosine is x, sine is y, cosine is x. And what we'll do is we're going to take this definition, this fact that happens to be true in the first quadrant, and extend it to all the other quadrants so that sine and cosine make sense no matter what our angle is. The angle doesn't have to be just an angle that's smaller than 90, which is how we've looked at it in the past in geometry, is that that angle only makes sense when it's an actual angle of a right triangle. But we're going to look at what happens when that angle keeps getting bigger, when it goes around the circle, or if the angle is even negative, and what happens. Okay. So this endpoint right here, x comma y, it's going to have coordinates cosine of theta. So I'll write it out, cosine of theta, comma, sine of theta. And so that endpoint depends purely on the angle theta. If you want to find the x coordinate, you take the cosine of that angle. If you want to find the y coordinate, you take the sine of that angle. And if you were to go backwards, it's also true. So if you know that point on the unit circle, then you know, and you know the angle, then you know cosine and you know sine for that angle because you know the two coordinates. All right, here's the unit circle definition for sine and cosine. It's wordy because we have to kind of build up this notion no matter what our angle is, okay? So, start off with an angle theta. Draw the corresponding radius for that angle. So that radius can land in quadrants 1, 2, 3, or 4. It can land in any of those quadrants, or it can be on the axes themselves, right? So we have many different radii that we could draw, and it just depends on theta, what that angle is. You draw that radius. Then xy, we're going to call that endpoint. That's the endpoint for that radius that's on the unit circle. So I can draw, this is my picture right here. We can call this guy x, y. That point right here has coordinates x, y. Then we define cosine to be the x coordinate. So cosine is the x coordinate for that point. Sine is the y coordinate for that point. So forget about the opposite over hypotenuse and the adjacent over hypotenuse. That just was kind of a stepping stone to get to this definition, which is a more extensible definition of sine and cosine. So that last definition only works and only makes sense when your angles are less than 90 and you have a physical triangle you're looking at. This definition now holds no matter what angle theta is. Theta could be 375 degrees, it can be negative 2 pi degrees, and whatever. So this holds for no matter what the angle is. Cosine is the x coordinate of the endpoint, and sine is the y coordinate of the endpoint. Okay, so that's our definition for cosine and sine. Based off your angle, draw the radius that corresponds to it. The endpoint, the x coordinate, so the endpoint on the unit circle, its x coordinate is cosine of that angle, and its y coordinate is sine of that angle. That's the unit circle definition. And that's the definition we're going to be using for cosine and sine for most of this unit. Later on, we're going to look at triangles again, and physical triangles, and then we'll not need to worry so much about this unit circle definition, but just this is the most powerful definition for cosine and sine. It allows the angle to be any angle, not just an angle that's less than 90 degrees. Okay, so let's go ahead and use this definition to compute some cosine and sine, some functions. So we're going to look at cosine of 30 degrees and sine of 30 degrees. So to start off with, we use the definition. We say, okay, I want to find cosine of 30 and find sine of 30. So I'm going to draw a 30-degree angle. So I'm going to draw that radius corresponding to 30 degrees. So if I sketch in my 30-degree angle and draw the radius, there's my radius. And from our work about unit circles, we already know the endpoint. We already know what the endpoint is because we've done so much work already around around these special right triangles, the 30, 60, 90, and the 45, 45, 90 triangles. So based off of what we've already done, we know the endpoint is square root 3 over 2, 1/2. I'm not going to go through deriving that again. You can watch the video about special right triangles that walks through why it's true. But that endpoint's coordinates are root 3 over 2, 1/2. And so based off of the 30, 60, 90 triangle that's there, we know cosine of 30 and sine of 30. Cosine 30, by its definition, is the x-coordinate. So I'm going to do a little color coding here, or do my best to. So cosine is the x-coordinate. This is cosine of 30 degrees. That side of that triangle. So cosine is square root 3 over 2. And then sine of 30 degrees, that's the y. So this is sine of 30 degrees. Right here, this length, and so it's going to equal 1/2. So cosine 30 is root 3 over 2, sine of 30 is 1/2, and you know these just by looking at the unit circle. So I'm going to be asking you to compute cosine and sine based off of the unit circle, because then you really understand these functions. If you use a calculator to compute cosine and sine, they're just random numbers, they're arbitrary. You know, you see point, 866, and you're like, oh, whatever. Okay, so that's 0.866. But it's square root 3 over 2, and that's fundamental to this unit circle and to this 30, 60, 90 triangle. Okay, so that's where these come from. Okay, we'll look at another example. Compute cosine of pi over 2 and sine of pi over 2. So we're going to draw the radius corresponding to pi over 2, radians. And note, when you see the angle without a degree symbol, you assume it's radians. So an angle with no degree is a radian angle. We're gonna so we'll draw on a pi over 2 angle. Recall that pi over 2 is half of pi, which is equivalent to 180. So boom, there's our radius. Our radius is going straight up. So I'll use blue for this. So our radius is straight up. Okay. So it's a 90-degree angle. It's pi over 2 radians. This is pi over 2. Okay, because this is pi. Half of pi is pi over 2, so pointing straight up. 180 is pi, half of pi is 90. Okay, so based off of what we know about this point, its x-coordinate is 0 and its y-coordinate is 1. Boom, we found the answer. Cosine pi over 2 is 0, sine of pi over 2 is 1. So when I know that unit circle really well, all of a sudden I can find cosine and sine very quickly. I just need to know the point on the unit circle that goes with that angle. Cosine pi over 2 is 0. Sine of pi over 2 is 1. Sine is the y, cosine is the x. Let's do one more example. Let's compute cosine of 7 pi over 6 and sine of 7 pi over 6. So cosine of 7 pi over 6, we need to draw this angle. Now this is a slightly trickier angle, 7 pi over 6 radians. Okay, so remember pi over 6 is 30 degrees. 7 pi over 6 is 1 whole pi and another sixth of pi. So that would be 7 sixths, because you have 6 sixths and 1 sixth. So we have pi plus pi over 6. So this is the same as 180 plus 30. So this is 210 degrees. Sketching that 210 degree angle, so here's 210 degrees. We recall, this is again a 30, 60, 90 triangle. Here's my 30 degree angle, boom, right there. And so I know the side lengths, I know the endpoint of this radius. I know this is going to be minus 1/2 in the y, and I know this is going to be minus root 3 over 2 in the x. So this guy's coordinates are negative square root 3 over 2 in the x, and negative 1/2 in the y. Therefore, cosine of 7 pi over 6 is minus square root 3 over 2. Sine of 7 pi over 6 is minus 1/2. Okay? So I know that they both have to be negative because we're in that third quadrant there, right? So the quadrants are labeled, I'll label them out, 1, 2, and 3. The third quadrant, and then this is the fourth quadrant. And in case you forgot about the signs of our points in these quadrants, we know in quadrant 1, both the x and y are positive. Quadrant 2, the x is negative and the y is positive. Quadrant 3, both are negative. And then in quadrant 4, the x is positive and the y is negative. So those are all the quadrants. And they're in this order because of the unit circle, because of how you travel around. 1, 2, 3, 4. That's how you move around the unit circle. In case you didn't know that. But anyway, coming back to this problem, cosine of 7 pi over 6, that's the same as cosine of 210, which is negative root 3 over 2, the x-coordinate. Sine of 7 pi over 6 is the same as sine of 210, and that's negative 1/2, the y-coordinate. Boom. Okay, lastly, let's talk about the Pythagorean identity. Recall that if xy is a point on the unit circle, if and only if it satisfies this equation, x squared plus y squared equals 1. So if you have two numbers that satisfy this equation, x and y, then you know it's going to be on the unit circle and vice versa. So this is going to lead us to an important identity that relates sine and cosine. Maybe you already see that identity. Maybe you've already seen it. Maybe you can just see where we're going with this one. We know cosine theta, sine theta is the point on the unit circle that matches to that angle theta. So when you draw your angle, you know cosine is the x-coordinate for that point and sine is the y-coordinate for that point on the unit circle. Therefore, cosine is my x, sine is my y. We get this identity, cosine squared of theta plus sine squared of theta is equal to 1, no matter what the angle is, because that point's always on the unit circle. This identity is always true. A note is that when we write the 2 in between cosine and theta, that means to take cosine of the angle and then square the answer. So it's a notation, and this is because we do this so often, we don't want to write parentheses again and again and again. So to simplify it and to remove all these parentheses, we put that 2 in between cosine and theta. That says take cosine, then square. So it's an order of operation things. Also, because this would look weird, cosine of theta squared. That looks like, and this is actually interpreted as square the angle and then take cosine. So this is not the same thing as cosine squared. Okay, so let's go ahead and use this identity to solve a problem. All right, so we'll start off with this frame. We say start with an angle theta, and we say let that angle be between pi over 2 and pi. So that angle is more than pi over 2 but smaller than pi. And then sine of that angle is equal to 3 over 5. So that's our starting off point. We know what the sine is and we know where the angle lives. We want to evaluate what cosine of that angle is. And we can do this without figuring out what theta is exactly. We can find what cosine is based off of the Pythagorean identity. Okay, so let's go ahead and start trying to figure this out. Based off of the first bit of information, so this part right here, we know that the angle is going to be in quadrant 2. So I'm going to just sketch it out. Here's my unit circle. So we know that theta is more than pi over 2. Here's pi over 2. And it's less than pi. So there's pi. So we know that somewhere over here is where my angle is. So theta is over here, somewhere in this second quadrant. So I already know from that my cosine of theta is negative. So because this is in the second quadrant, where the x's are negative, the cosine of this angle is going to be negative as well. So that's something to keep in mind. We'll see where that pops up in the answer a little bit later. We're going to use the Pythagorean identity. We know the sine of theta is 3/5. So let's use that fact in a second. So the Pythagorean identity says cosine squared plus sine squared is equal to 1 for any angle. So we know what sine of the angle is, so we'll substitute in sine of theta equals 3/5 into my Pythagorean identity. This tells us cosine of theta squared plus 3 over 5 squared is equal to 1. Now we have one equation that has cosine in it, an unknown, and just numbers. We can solve this. We're going to square 3 over 5. That's going to give us 9/25. Subtract it from both sides. So 3/5 gives us 9 over 25. And subtract that from both sides, we get 1 minus 9 over 25. That's 16/25. Taking the square root now of both sides reveals what cosine is. Seems like cosine is either positive 4 over 5 or negative 4 over 5. It can't be both because we've locked down that angle into one quadrant. So what will the answer be? Is cosine positive 4/5 or is it negative 4/5? Remember what I said earlier? We know the quadrant, so we know the sine of the angle, or we know the sine of cosine. Because it's in quadrant 2, we know the cosine is negative. So we throw away 4 over 5. It's an extraneous answer. And so the answer must be cosine of theta equals negative 4/5. And so that tells us the cosine of the angle without actually having to know what the angle is exactly in degrees. All we needed to know was sine. Okay, so we can solve problems like this. We just need to figure out what quadrant our angle is in and use the Pythagorean identity to determine what the cosine or sine is, depending on what you're solving for. And that's it. That's all I wanted to show you guys in this video. And we'll get some practice solving these kinds of problems, as well as computing cosine and sine based off the unit circle in the next worksheet. Next time, the next video, we're going to take a look at tangent as the slope of radii. So we spent already some time talking about slope. Now we're going to see why we spent that time talking about slope, because it turns out that's a really nice way to describe what tangent is when we get to it. So with that, I'm going to leave you guys and sign off. I'll see you guys next time.